Welcome back to lecture 6.2, where we're going to talk about our work using our 3D equation of state. Okay, so last time we derived our three-dimensional equation of state. And we looked at it a little bit. We had beta v dt minus kappa v dp. And we said we'll definitely need to integrate this properly, and we will have to, look at the temperature dependence or pressure dependence of the kappas and the betas in doing this. Okay, so we arrived at this partially by just writing down our differential equation, our partial derivatives. So this was partial v, partial t at constant p dt plus partial v, partial p at constant t dp. So we talked about this last time, right? Just writing down this differential. Okay, so the question now this time is, can I write dw is partial v, partial t, partial w, partial t at constant p dt plus partial w, partial p t dp. So can I write this? Is it equivalent, to be able to write that? And the answer is no. This is not okay. Right? Our volume was a state function, right? Our volume was determined identically by temperature and pressure. Think back to that three-dimensional graph where we had, for example, x and y and f, right? And if we had some point x, y, it uniquely defined where f was, right? So f of x and y had a unique function, right? F was a state dependent only on x and y, right? W, the work, is not like that, right? I can't define the temperature and the pressure and tell you the work. Oh, excuse me. These are not the times when one is supposed to be sneezing. All right, so we cannot define the work simply by telling you what the thermodynamic variables are. I have to tell you. So work depends on path, right? Work depends on the path. So what I can instead write is dw, right, is equal to minus p dv. And this can be minus p beta v p dt plus kappa v p dp, and hence the work would be the integral minus from t1 to t2 of beta v p dt plus the integral from p1 to p2 of kappa v p dp. Right? That is, the work depends on the path I take to get there. How I evaluate this integral, right? I'm going to evaluate this integral going from here to here, here to here, right? I even may need to break it up into chunks. May need to do this part, and then that part, and then the next part, right? Like we've been doing with our work. So we're going to, in class, work out some examples. Work out some examples of this work. Okay? The work done as we do various processes. We're going to heat and compress a liter of mercury. We're going to heat mercury at a fixed volume. We're going to heat it at a fixed pressure. We're going to compress and at a fixed temperature, and we're going to see the various works that happen when we do that. Okay. So just one more point I want to make on this in this lecture is that this is not the we've talked about work here coming from volume changes, right? But is there any other form of work? Well, for sure, we could have done work on a one-dimensional system, right? So this should be minus F dl, right? When we had our simple one-dimensional system, right? L, I fixed it at a point, I applied a force, for example. I move it some distance, dl, right? I'm going to change its distance. Remember how dl depended on L, so it was L. So it was very similar to this, right? It was L alpha dt. And was it plus or minus plus L over A y df, right? So our work, dw, I think it should be minus. That is, if I compress the force, I make this smaller, I should have, so if I, it depends on the sign. If I say that this is negative when I make it smaller, then this is negative, then this would be, make this positive. So the work would be work on, right? So dw would be minus F L alpha dt minus F L or A y d. Just thinking about pressure, df, right? So the point here is that we're doing work on the system like by mechanically changing its configuration. So another way we can say this is that these are all forms of configurational work, right? They're all mechanical, but they all depend on changing its shape, changing its volume, changing its length, right? These are configurational forms of work. These we cannot define in this way. So cannot define in the ways we've been talking about, so-called dissipative work. Right? So we can't define in this way things that are dissipative work. Like, so imagine the friction of moving something along a plane, right? We would have some dissipation, and we cannot define dissipative work in that way, right? And so this is going to allude to next time, where we're going to talk about some more about these kinds of dissipative work. So eventually we're going to talk about dissipative work and how we do define it. Okay, thank you.